Welcome! In this video, we'll show how to model and simulate a DC-DC buck converter with Altair Activate and its integrated SPICE simulator, HyperSpice. We'll first review basic facts about the DC-DC buck converter circuit. Then enter the schematic with Activate and simulate and analyze the results. The DC-DC buck converter provides an output DC voltage supply lower than an input DC voltage supply, for instance a 3 volt output from a 19 volt input. This power conversion is highly efficient and is frequently used in many applications like computers, mobile devices and automotive. The basic circuit features a switch that might be a power MOSFET or an IGBT, a freewheeling diode, an inductor and an output capacitor. The proper design requires a good accuracy of the components models, and SPICE models are therefore the good choice. The operating principle is based on two phases. During the first phase, the switch is on and energy is injected in the inductor, the current in the inductor increases and the diode is reverse biased. The current flows from the input supply through the inductor, the load and capacitor, and back to the input supply. During the second phase, the switch is off. The inductor provides now the energy and its current decreases. The diode is forward biased. The current flows from the inductor through the load and capacitor and through the freewheeling diode. The main operating parameters are the switching frequency with a period Ts, the duty cycle D, a number between 0 and 1. During a time of D times Ts, the switch is on and off during the rest of the period. When the steady state is reached, if a sufficient current is drawn by the load and with ideal components, the output voltage is related to the duty cycle and the input voltage by the equation Vout equal D times Vin. In an open-loop operating mode, D is fixed, but there are several drawbacks like incorrect output voltage or poor dynamic response. A feedback control is added to provide a closed-loop operating mode. D is then adjusted continuously to compensate the component's non-idealities, input voltage variations, and improve the dynamic response. We will now implement the open-loop circuit with Activate by using full accuracy SPICE models and the SPICE simulator integrated into Activate, HyperSpice. First, let's add the standard components in Activate modeling window. We go to the HyperSpice analog basic palette, put a ground, a voltage constant, its parameter value, then pick an inductor, the output capacitor, and the load resistor. then connect all the components together. Now, we add a diode that is described in a separate file as a spice.model. Such files may be provided by third parties like electronic components manufacturers. We pick the diode symbol in the Spice palette and we put the name of the model SBD for a Schottky diode, and we must add a reference to the file in the form of an include block, and then we put the name of the file that describes the diode model. So here it's Schottky diode.lib. This file is placed in the same directory as the Activate model. Then we connect the diode. Now we add the power MOSFET described in a separate file as a spice.subsckt. This is another form of component model provided by electronic components manufacturers. Check the order of port names that will be used later to connect the MOSFET to the circuit. We select an instance block from the palette. We put the name power underscore MOS, that is the name of the subsckt, and we add two output ports on the right of the block. And we must also provide a reference to the file that describes this power MOSFET. So here the file name is power underscore mos.lib and is in the same directory, and we connect the drain, the source port, and finally we add the switch control circuit implemented with a voltage pulse with several parameters that will be entered later in a script. And we also add a resistor that will be connected to the gate of the power MOSFET. Okay. We have now our DC-DC buck converter model. Let's simulate it. First, we are adding an Activate scope block to display the result waveform. We go to the HyperSpice analog interface palette to find various sensors. So first, a current sensor that will put in series with the inductor to probe the current through the inductor. The proper orientation, and we also add several potential sensors. And the voltage sensor to probe the power MOSFET control signal between gate and source. In the Activate Signal Viewers palette, we find the scope block. So do the several connections. We'll set the waveform names. Now we go to the model script window to enter all the parameters. So first the voltages, input voltage, output, so the duty cycle, the switching frequency, 10 kHz, so the switching period, the gate control voltage, the rise and fall times, and the pulse width, and several component values, and also the final time of the simulation. Okay, let's launch the simulation now. Very fast. We'll have a look at the results. So the gate control signals, the power MOSFET source signals, so the inductor current that rises when the switch is on and decreases when the switch is off, and we can see also the output voltage with a rather large ripple between maximum and minimum during the steady state. We can also see the settling time of the buck converter, so here on the inductor current and also on the output voltage at the beginning of the simulation. Activate provides also nice features to compute and display interesting values during the simulation. We are going to use some of them to display the output voltage ripple during steady state. So we add a mean over interval block, a max over interval block. So this will be used to compute the minimum and maximum values of the output voltage during the steady state. And to trigger the start of the measurement, we add an event time block, and we set the event time instant to a parameter t steady, so that the measurement occurs once the steady state is reached. Now we'll add display blocks from the signal viewers palette to see the minimum and maximum. In the Activate math operation palette, we find the sum block that will allow us to display the output voltage ripple. And finally, we define the testED value in the model script. Now we can launch the simulation again. Okay, so the same ripple, and here we see it's 300 millivolts. So we'll change the switching frequency, increase to 100 kilohertz, and see now the new results. So now it's the ripple, it's far better with only 15 millivolts. But we can see that the output voltage is less than 3 volts due to components non-idealities. With Activate, we were able to develop a model of the DC-DC buck converter with SPICE-level accurate results. For further information, please check out our site forum.altair.com. Thank you for your attention.